a complex number is written in the form a plus iota b, where a and b are real numbers and iota is the imaginary unit defined as the square root of -1. The modulus of a complex number z equals a plus iota b, written as modulus z, is defined as the square root of the sum of the squares of the real and imaginary parts. The modulus represents the distance of the complex number from the origin in the complex plane, also called the Ergin plane. For example, if z equals 3 plus 4 iota, then modulus z equals the square root of open bracket 3 squared plus 4 squared close bracket, which is square root of 9 plus 16, equals square root of 25, which is 5. The conjugate of a complex number z equals a plus iota b is written as z bar equals a minus iota b. The conjugate works by changing the sign of the imaginary part while keeping the real part unchanged. For example, if z equals 3 plus 4 iota, then its conjugate is z bar equals 3 minus 4 iota. The conjugate is particularly useful in simplifying complex expressions, especially when dividing complex numbers and solving equations. It helps remove the imaginary part from the denominator, making the expression easier to work with. Some important properties connect modulus and conjugates. First, the modulus of the conjugate is the same as the modulus of the original complex number. In words, modulus of z bar equals modulus of z. Second, multiplying a complex number by its conjugate gives a real number. In words, z times z bar equals a squared plus b squared, which is the same as modulus z squared. Third, the conjugate of a product is equal to the product of the conjugates. In words, conjugate of z1 times z2 equals conjugate of z1 multiplied by conjugate of z2. For example, let z equal to plus 3 iota and w equal 1 minus 2 iota. Then z times w equals open bracket 2 plus 3 iota close bracket times open bracket 1 minus 2 iota close bracket, which simplifies to 8 plus iota. Their conjugates are z bar equals to minus 3 iota and w bar equals 1 plus 2 iota. When dividing complex numbers, we use the conjugate of the denominator. If z1 equals a plus iota b and z2 equals c plus iota d, then z1 divided by z2 equals open bracket z1 times conjugate of z2 close bracket divided by open bracket z2 times conjugate of z2 close bracket. Let's see an example. Divide 3 plus 4 iota by 1 minus 2 iota. Step 1. Multiply numerator and denominator by the conjugate of the denominator, which is 1 plus 2 iota. Step 2. Simplify the expression. Another important property, the modulus of the quotient is the quotient of the moduli. In words, modulus of z1 divided by z2 equals modulus of z1 divided by modulus of z2. Let's try a more advanced example. Problem: express open bracket 5 minus 3 iota close bracket to the power 3 in the form a plus iota b. Solution: expand using binomial expansion. That is, open bracket 5 minus 3 iota close bracket cubed equals 125 minus 3 times 25 times 3 iota plus 3 times 5 times open bracket 3 iota squared close bracket minus open bracket 3 iota close bracket cubed. Simplifying step by step, the result becomes negative 10 minus 198 iota. Its conjugate is negative 10 plus 198 iota. Now, let's calculate its modulus. Modulus equals the square root of open bracket negative 10 squared plus negative 198 squared close bracket. That is the square root of 100 plus 39,204, which equals square root of 39,304. Let's recap. We explored two key ideas, the modulus and the conjugate of a complex number. The modulus gives the magnitude or distance of the point from the origin in the Argand plane. The conjugate flips the sign of the imaginary part and is especially useful in division and simplification. For example, if z equals to plus 3 iota, then modulus z equals square root of 13 and the conjugate z bar equals to minus 3 iota. Together, these ideas form the foundation for many operations in complex numbers. I hope you now clearly understand how to work with the modulus and conjugate of a complex number. See you in the next topic.